There have been a wealth of neurotransmitters identified, and I bet there's still more out there that we haven't identified. The three neurotransmitters on this slide, norepinephrine, dopamine, serotonin, are the ones we're going to focus on, along with epinephrine and acetylcholine, which we will see when we address the autonomic nervous system in a later chapter. We have previously discussed the effects of acetylcholine on skeletal muscle. However, ACH is also used as an excitatory neurotransmitter in the brain. As you can see from the description of dopamine, a neurotransmitter can be both excitatory and inhibitory. Its effect is determined by the type of protein receptors it connects with on a target organ. I like to include serotonin in my explanations of the nervous system because so many of us these days are on SSRIs, SSNRIs, myself included. These drugs, called selective serotonin reuptake inhibitors, they focus on making serotonin more available to make action potentials. So drugs such as Lexapro, Cymbalta, and many, many other entry-level antidepressants are SSRIs. There are also SSNRIs, such as bupropion or Wellbutrin, and these work on serotonin and norepinephrine. In low dosages, SSRIs and SSNRIs especially can act as painkillers, especially for back issues. Do you see what it says in the middle here, where all three of these neurotransmitters overlap? It says happiness, right? Happiness is thought. How about contentment? Is thought to be an agreement among these three neurotransmitters. And this is why so many antidepressants out there target these three neurotransmitters. Okay, so these three neurotransmitters here, dopamine, norepinephrine, and epinephrine, they belong to a structural group called catecholamines. So that has something to do with how their structure of atoms are. These neurotransmitters, though, they have similar building blocks. The lines in these pictures trace the pathways of neurons that have protein receptors for these neurotransmitters. Norepinephrine seems to invade the cerebellum, whereas epinephrine and dopamine do not. SSNRIs that target norepinephrine are known to work on pain of the lower body skeletal muscles and are a drug of choice for back pain. Take a look at what epinephrine does, only innervating the brain stem and the diencephalon, whereas we have dopamine also invading your cerebrum. Let's take a closer look at serotonin, and let's use it as an example to learn about how a neurotransmitter is removed from a synapse. Why would you want to remove it? So you can stop the depolarization in the postsynaptic neuron. You know, the purpose is not always to excite the postsynaptic neuron. It might be to excite it for a little bit and then stop exciting it. As you can see in the picture on the right, we have a presynaptic neuron coming down from the top of this picture in purple, and we have a postsynaptic neuron coming up from the bottom of this picture in blue. Serotonin is diffusing across the synapse and connecting with those receptors that are on the postsynaptic neuron. These are the receptors on the postsynaptic neuron. At some point, those receptors will start to spit the serotonin back into the synapse. It's like, blah, thank you, I did what you told me to do. Blah. At that point, serotonin can start to just diffuse away from the synapse, like just kind of like wander away. Or it can be broken down by an enzyme, or it can be sucked back into the axon terminal of the presynaptic neuron through a protein channel that's called a reuptake transporter. On the left side of this little picture right here, you can see serotonin, and a reuptake transporter, putting the serotonin back into the presynaptic neuron and reloading it in a vesicle just so it can be used again. There is no picture on this picture of an enzyme breaking down a neuron, so I'll just draw a little picture of Pac-Man there. He's basically, or Miss Pac-Man, or just Pac-Person, is basically gobbling up all of the serotonin. On the right side of this presynaptic neuron, you can see that one of these reuptake proteins is being inhibited. By blocking the reuptake transporter, serotonin will spend a longer time in the synapse, and it'll increase the probability that serotonin will bind to a receptor on the postsynaptic neuron and cause an action potential. This is exactly what the class of drugs SSRIs does. According to its name, these drugs are selective to serotonin, and they inhibit the reuptake. As you can imagine, an SSNRI, it does the same thing. However, it is selective not to serotonin or epinephrine, but norepinephrine. If you compare the picture of the brain in this slide to the pictures in the previous slide, you'll notice that serotonin pathways are much more numerous than the pathways of the other two neurotransmitters. This increased abundance also leads to SSRI drugs being an entry-level drug with very low side effects, but also the greatest extent of an effect on neurons in the brain because it's targeting a neurotransmitter that has more pathways in the brain than the other two. Neuromodulators don't cause or prevent action potentials, nor do they cause postsynaptic potentials. Neuromodulators are capable of increasing the release of a neurotransmitter from a presynaptic terminal in an effort to encourage an action potential in a postsynaptic neuron. They can do this by increasing the sheer number of neurotransmitters from a presynaptic neuron, or they can do this by increasing the rate of release, making it much faster. In contrast, neuromodulators can also allow neurotransmitters to function normally in the synapse, but the neuromodulator alters the ability of the postsynaptic neuron to respond. No, they don't do this by blocking the protein receptors. They're a little bit different. They don't alter the activity of the neurotransmitter. But what a neuromodulator can do is prevent the postsynaptic cell from having an action potential. And what it does is it'll force the cell to depolarize just a little bit, but not enough. Opioids do this. They prevent a full action potential from carrying information about pain from being sent up your spinal cord into your brain. Your tissues are in pain. You are ignoring the pain signal, most likely doing damage to those tissues because you can't feel them and you're overworking them, right? So your tissues are in pain with opioids, but your brain is not hearing their screams. And this is why I'm not saying that opioids are bad. They're what some people take and work great for them. But this is also why opioids, they can lead to more injuries because you're kind of fooled into thinking that you're not in pain, but you are certainly impaired.